The nuclear magnetic moment is the magnetic moment of an atomic nucleus and arises from the spin of the protons and neutrons. It is mainly a magnetic dipole moment. The quadrupole moment does cause some small shifts in the hyperfine structure as well. All nuclei that have non-zero spin also possess a non-zero magnetic moment, and vice versa, although the connection between the two quantities is not straightforward or easy to calculate. The nuclear magnetic moment varies from isotope to isotope of an element. For a nucleus of which the numbers of protons and of neutrons are both even in its ground state, the nuclear spin and magnetic moment are both always zero. In cases with odd numbers of either or both protons and neutrons, the nucleus often has non-zero spin and magnetic moment. Measurement methods. The methods for measuring nuclear magnetic moments can be divided into two broad groups in regard to the interaction with internal or external applied fields. Generally, the methods based on external fields are more accurate. Shell model. According to the shell model, protons or neutrons tend to form pairs of opposite total angular momentum. Therefore, the magnetic moment of a nucleus with even numbers of each protons and neutrons is zero, while that of a nucleus with an odd number of protons and even number of neutrons will have to be that of the remaining unpaired nucleon. For a nucleus with odd numbers of each protons and neutrons, the total magnetic moment will be some combination of the magnetic moments of both of the last unpaired proton and neutron. The magnetic moment is calculated through J, L and S of the unpaired nucleon, but nuclei are not in states of well-defined L and S. Furthermore, for odd nuclei, there are two unpaired nucleons to be considered, as in deuterium. There is consequently a value for the nuclear magnetic moment associated with each possible L and S state combination, and the actual state of the nucleus is a superposition of these. Thus, the real nuclear magnetic moment is between the values associated with the pure states, though it may be close to one or the other. G factors. The values of G and G are known as the G factors of the nucleons. The measured values of G for the neutron and the proton are according to their electric charge. Thus, in units of nuclear magneton, G equals 0 for the neutron and G equals 1 for the proton. The measured values of G for the neutron and the proton are twice their magnetic moment. In nuclear magneton units, G equals minus 3.8263 for the neutron and G equals 5.5858 for the proton. Calculating the magnetic moment. In the shell model, the magnetic moment of a nucleon of total angular momentum J, orbital angular momentum L and spin S, is given by projecting with the total angular momentum J has contributions both from the orbital angular momentum and the spin, with different coefficients G and G. By substituting this back to the formula above and rewriting for a single nucleon, for we get and for bibliography. Nersesov, E.A. Fundamentals of Atomic and Nuclear Physics. Moscow. Mir publishes. ISBN 5-06-001249-2. Vonsovsky, Sergei V. Magnetism of Elementary Particles. Mir publishes. Hans Kopfermann Kernmomenta and Nuclear Momenta.